Okay, so let's get started on the last lecture of this series. So we are trying to prove, let us recall, Hormander's theorem, or one of Hormander's several theorems, or one of many theorems named after Hormander, however way you interpret that, which in one version says the following. So omega is a smoothly bounded pseudo-convex domain in Cn, and phi in C2 omega bar strictly pre-subharmonic function and you look at the number C, which is the infimum over all points in omega of lambda 1, where lambda 1 is the smallest eigenvalue, lambda 1 of A is the smallest eigenvalue of the Hessian of the pre-subharmonic function phi at A. So therefore it is some non-negative real number, positive real. Assume that C is strictly greater than 0. So this is what it is. So, and then for every G in L2 PQ omega, where Q is greater than or equal to 1 and d bar G is equal to 0, there exists a U in L2 PQ minus 1 omega such that d bar U is equal to G, and we have by now familiar estimate integral length of U square e to the power minus phi dV is less than or equal to 1 over C times Q, where Q is this degree, length of G squared e to the power minus phi dV. So this is the theorem. So by now we have already established the basic a priori estimate. So we already know that for every alpha which is in C infinity of degree 0 Q, so we'll assume P equal to 0 without any loss of generality, okay, as usual. So for every C infinity form up to the boundary which also belongs to the domain of d bar star, recall that this involves the vanishing of certain a component of the form in a certain direction along the boundary, along the normal direction. We have the estimate norm of d bar star alpha phi squared plus norm of d bar alpha phi squared is greater than or equal to H phi, excuse me, acting on alpha and alpha in phi. This is what we have seen. Now for one forms, it's obvious. For one forms, 0, 1 forms, it's clear that H phi alpha comma alpha, this is bounded below times norm of alpha squared, right? Because the C is the smallest eigenvalue, right? You are of this quadratic form with respect to the ambient quadratic form, and therefore this is what it is. And if you write out what exactly this thing is and work it out completely, you realize that for 0 Q forms, a Q enters here. There are several pieces there. So therefore, what I have is I can replace this by q times c times norm of alpha phi squared. Factorial, yes. Yeah, yeah. I'm thinking of going your way soon, but this is too short time to make a change of notation. Yeah. Okay. So skipping that kind of uninformative computation, I have what I basically need. Okay. The other component I need to complete this argument would be the approximation result. Okay. So what is the result that we need? So we need that for all alpha that belongs, observe here, and this was already there, so I'm kind of repeating what George did, so I'm taking advantage of the fact that we have already gone over these things before. So this alpha has to be in the domain of d bar star and the domain of d bar in different degrees, right? So domain of d bar star intersection domain of d bar intersection L2 PQ omega phi. Okay. There exists. So I will let me first write it down in complete detail, and then let me use the buzzword. There exists a sequence of forms alpha j, or maybe I'll call it alpha nu, because yeah, alpha nu in L2 PQ omega phi, such that three things must happen simultaneously. Alpha nu must go to alpha in L2 PQ omega phi. D bar alpha nu must go to d bar alpha in L2 PQ plus 1 omega phi. And last but not the least, alpha star, d bar star alpha nu must go to d bar alpha in L2 PQ minus 1 omega phi. Or if you want to avoid so much things, you want to say, what did I do here? Excuse me. This of course exists. This is not a big deal. And this p is always 0. That was another mistake I made. C infinity 0 q omega bar intersection domain of d bar star. So you want a sequence which is in the domain of d bar star and smooth up to the boundary so that these things happen. Okay? Or that is the same thing in a different language. The C infinity 0 q omega bar intersection domain of d bar star. C infinity d bar star is dense in domain of d bar intersection domain of d bar star in the graph norm. So the graph norm is associated with a particular operator. In this case, you can think of this operator either as the Laplacian or as the direct sum. So this is sort of graph norm of this. That is, the norm of u is given by norm of, so this is the graph one, of course, is given by the L2 norm of u squared plus the L2 norm of d bar u squared plus the L2 norm of d bar star u squared. Observe that these are actually different L2 spaces of different degrees. Is that clear? So this is what I need. And in fact, this is a correct and difficult theorem, somewhat difficult theorem. I will explain a little how this is done. So please believe it. The way one does it, and I can give you precise references, is one has to, so the real problem here is that as you approximate, you want to maintain this condition that it lies in the domain of Debraj star, which is basically the vanishing of a certain linear combination of these things, okay? Which is what makes it much, much more difficult for the corresponding statements for either domain of Debraj or domain of Debraj star. So the crucial idea is to split the forms up into pieces and to modify them separately, and then apply something called Friedrich's lemma, which allows you to sort of compensate the mistakes that you made. Okay, so that doesn't make much sense, but that is what it is. However, I'll now take tell you a joke about this. I cannot yeah. So it is said, I don't know, this may be apocryphal, that Jimmy Carter, the US president, after being defeated by Reagan, like past presidents, they keep on giving like this commencement talks, convocation addresses. He went to Japan, and like when you begin, you tell some funny stories about yourself and stuff like that. And there was an interpreter who was explaining things to the audience. So he spoke for about 5 to 10 minutes, and then the interpreter just said 2 sentences. It was a funny story, and everybody started laughing. At the end of the commencement speech, he went and talked to the interpreter and said, well, this Japanese must be a very expressive language, because I spoke for like 5 minutes and you were able to convey the story only in 2 sentences. He said, no, that's not what I said. I said that Carter-san here has told us a very funny story. It's now time to laugh. So, similarly, I have given you a correct and difficult theorem. This is correct. So once you have this, so it follows that, so just by taking limits here, you start with your alpha, then you take the approximating sequence alpha nu and take the limit. So it follows that for all alpha in domain of D bar intersection domain of D bar star, we have D bar star alpha phi squared plus D bar alpha phi squared is greater than or equal to Q times C times norm of alpha phi squared. If you have been following these lectures, at this point the theorem is as good as proved, because this is the fundamental basic estimate that already implies the theorem. So what I will do now is very quickly follow through Draw's argument just an hour ago to complete the proof, just for completeness. Okay, so all you need to do is to apply the function analysis lemma. For this, I will take H1 and H2. Now I do need them to be different spaces. H1 would be therefore L2 P Q minus 1 omega phi, and L2 will be the kernel of D bar in the next degree. This is always 0. That's just Q, thank you. And this, as Draw already remarked, is closed because, see, if D bar were a continuous operator, then its 0 set is of course closed, but it's also true if D bar is just a closed operator, and that's very easy to see. So this is closed since, okay, let's take a sequence Fj in the kernel of D bar such that Fj goes to, let's say, F in L2 0Q omega, but then observe, but then if you look at D bar Fj's, they are equal to 0. They convert to 0 in L2 0 Q plus 1 omega. So by definition of closeness, we note that F equal to D bar F equal to 0, which means that this kernel of D bar is closed. Okay? Okay, so we have the up spaces, and then uh, then for all alpha in H2, we have norm of Debraj star alpha. So on H2, this guy is 0, of course. Squared is bigger than or equal to Q times C times norm of alpha phi squared. Okay, and we see. I think I'll just stop here, and you see now how to complete this, right? Okay? Using the functional system. Okay? So therefore, modulo some correct and difficult theorems, we have actually proved Hörmander's theorem. So what we do next, I think we have a little time. First of all, I'd like to point out an important consequence of this thing. So many of these hypotheses are actually redundant. Okay, so this pre-subharmonic function can be taken to be much general. I don't really need strictly pre-subharmonic and so on. The one that I want to concentrate on, and which is kind of important in applications, is that I really don't need omega to be smoothly bounded. So let me try to explain what to do if omega is not smoothly bounded. So first of all, I will remove this weight altogether. Okay. So I'll state this as a corollary. And this corollary would be also familiar to you from the one variable situation. So let omega subset of Cn be a bounded, this is extremely important, pseudo-convex domain. And I made a small mistake last time. I put a 1/2 where it did not belong, but this time I'll do it correctly. Let delta be the diameter of omega. And now, what you want to do is you want to take a G. So for all G, which are just in L2, I can even say PQ of omega, with Q greater than or equal to 1 and D bar G equal to 0, there exists U. Q greater than or equal to 1, thank you very much, Q greater than or equal to 1, yeah. All indices are automatically greater than or equal to 0, right? Nothing to be said there. L2 P Q minus 1 omega. So that the two desirable things happen. D bar U is equal to G, and the L2 norm of U is, I'll just write it this way, L2 norm of U is bounded by, so I even know the constant up to some degree of accuracy, the square root of epsilon times delta divided by Q. So it is controlled only by the diameter of this set times the length of G. Okay. Is this clear? So I have actually honest L2 estimates, unweighted ones. And by now the proof of this should also be very familiar. So step 1. So in Hormander's theorem, in the theorem on the first board, in the theorem just proved, take without loss of generality, assume that the domain omega is contained in the ball centered at 0 radius delta. So last time I said that you can actually put it in 1/2 the diameter. That is not quite right. You need to take the full diameter there. Okay. And yeah. That doesn't matter really, but I think somebody gave me an example in which it is, you can always take half the diameter.
Yeah, so just translate it.
So if you have something like that, okay, all right. So you can put it. So delta, okay, delta is not the diameter. Delta is the size such that you can translate it so that it belongs to the ball of radius delta. Most likely it is the half the diameter. That's what I think. Yeah.
If you take that triangle with same side equilateral triangle force,
Let us take that. That's kind of an interesting statement. Okay, suppose you take a triangle of equal sides 1. Okay, so the diameter of this guy is therefore 1/2. Diameter is 1, but you cannot put it in the.
Oh, that's what you're, oh, for me with the answer. Twice the radius of the smallest volume.
Oh, so then okay. Okay, doesn't matter. Yeah. Okay, so some data which does this. So without loss of generality, assume that omega is contained in this, and take phi of z to be 1 over delta squared times length of z squared, which is to say in this case mod of z1 squared plus mod of zn squared. In this case, of course, the Hessian is quite easy to see. The Hessian at any point is just the identity matrix, and there's a 1 over delta square here. Okay, and I think I'm not going to repeat this argument because we have done this explicitly for n equal to 1 already. So it follows, or maybe one can just plug into the formula. There exists u in L2 pq minus 1 omega phi, which is, because of the boundedness, exactly the same as L2 pq minus 1 omega, such that d bar u is equal to g, and you have this estimate there is the q somewhere, so 1 over cq, so that gives me, I think, delta square over q integral length of g square e to the power minus 1 over delta square mod z square dv. So this is therefore less than or equal to this delta squared over q times the norm of g squared, and this thing is obviously on omega greater than or equal to, so you can pull the smallest value of this out. So this is going to be 1 over e times the length of u squared, and you got what you wanted. Is that clear? Yes. So let us look at this number here. So what is this number? Say that again. Which estimate? This one? Because omega is contained in B0 delta. In order to assert the existence of the solution U. So omega is contained in B0 delta. I use the theorem in the first. Yes. Yes. I don't get it, because the okay. Yes. Yes. I said that without in the theorem just proved whether. So the statement is like is a bounded. Right now it is smoothly bounded, but still pseudo convex. Omega is still. Because otherwise, this is how I got the solution U.
Don't have this U, not pseudo.
The solution I got by using the theorem there. The solution U is coming from Hormander's theorem. There is no psi here. Phi. Oh, psi is like the psi is abbreviation for pseudo.
Okay.
Yeah, psi is just abbreviation for pseudo.
The function P
Yeah.
is a Corollary function in column radius 0 delta.
In the whole of Cn, if you want. Yes. Yes. So omega is a pseudo-convex domain. So the corollary is let omega be a bounded pseudo-convex domain and delta is its diameter. Then for every g which is square integrable on the domain, I can find a u which solves the equation and has this estimate. So it is sort of a variation on that where there is no weight, but the domain has to be assumed to be bounded, and I have removed the boundary smoothness assumption. Yeah. So here I am assuming the domain to be still smooth, but I wanted to point out what we have found here. So this number is therefore a lower bound on the eigenvalues of the Laplacian, of the box Laplacian, and it depends only on the diameter. So that is something very significant. But once we have that, this is a different theorem in which there is no phi. And this is a different result in which there is phi. In order to prove that, I used the first theorem with phi equal to 1 over delta squared times mod z squared. Oh, p. Yeah, I'm taking p to be p. Okay, yeah. It really doesn't matter. The p really doesn't matter what it is, because you just take some copies of L0q and add them up. That's what LPQ is, right? Yeah. So finally, now let omega be just a bounded pseudo-convex domain. And now I will write it in complete pseudo-convex domain. Okay. Now I can exhaust. So this omega can be written as the union of omega j's, j going from 1 to infinity, where this omega 1 contained in omega 2 and so on, these are smoothly bounded. So this is because, as we saw, omega has a strictly pre-subharmonic, if you want, exhaustion function. You take their sublevel sets, most of them will be smooth by Sard's theorem. So that is one way of seeing that. Okay, and once we have that, what we are going to do is an analog of what George did using Aloglu's theorem. So by previous part, on omega j, there exists uj, which is in L2 of omega j and phi, such that there is just no phi anymore, which is just in L2 omega j, such that d bar of uj equal to g on omega j, and we have the estimate length of uj squared is less than or equal to square root of e times delta j, you understand this notation, divided by q, length of g, there's no square anymore, g. This is the L2 norm on omega j, but this is for every j bounded by square root of e delta over q times the norm of g on the whole of omega, right? Now what you do is, so define, let's call this uj tilde to be uj on omega j and 0 on omega minus omega j. So these uj tildes are of course in L2 of omega, and they have a uniform bound. And now you apply Aloglu to them, and they will have a limit, and that limit will be the solution that we are looking for. Is that completely clear? Okay. Observe the crucial importance of the fact that we know that this constant depends only on the diameter, or at least it is bounded if we know the diameter is bounded. Okay. All right, I think that is basically what I wanted to say about pseudo-convex domains. So I have a few, like 25 minutes left or slightly less than that. So let me make a few comments about certain other things associated with this. For example, what happens on non-pseudo-convex domains? It's not true. Which one? The main one or the corollary?
Main one.
Main one, I didn't assume that omega was bounded. Oh, so that means with smooth boundary. Thank you very much. I have to. My language needs correction. Yeah, by smoothly bounded, it means that the boundary is smooth. You know? Yeah. With smooth boundary. Thank you very much. Yes. Yeah. Yeah. The second one, by the way, is false for unbounded domains in general, and it's an interesting exercise to find a counterexample. So where was I? So in general, for non-pseudo-convex domains, you don't expect either, in general, either solutions to the D-bar problem, or even if you find solutions, you might not have estimates. Okay. So one way to understand that is to, or one way to formalize that is to introduce the so-called L2 cohomology. Now, today I looked up the spelling. I will not make a mistake. So this is simply, for a particular degree PQ, the kernel of the D-bar operator as it maps L2 PQ omega, and these dots mean that we are dealing with like a dense subspace, to L2 PQ plus 1 omega, divided by the image of D-bar in L2 PQ minus 1 omega to L2 PQ omega. Right? So therefore, the corollary can be stated in a slightly fancy way if you want. It states that if omega is bounded and pseudo-convex, with your permission I am again using this psi, convex, then for all q greater than or equal to 1, this group HPQL2 omega is actually 0. Okay? Now, observe, of course, this is a vector space. Kernel of D-bar, in fact, is a Hilbert space, as we just saw, right? It's a closed subspace of a Hilbert space. And you are going mod a certain subspace. So you are taking a Hilbert space and quotienting by a subspace. Okay? What happens? So if we are taking a Hilbert space and going mod a subspace, how can you describe the result? So, yeah, I'm just waiting for somebody to say that. So what is the Hilbert space mod a subspace? So, okay, let me give the answer, okay. So if the subspace is closed, so let's see. Absolutely, provided that the subspace is closed. Okay, so there are two cases. Yeah, so suppose we have H, suppose H is a Hilbert space. H Hilbert space and S a subspace. If S is closed, then H mod S is naturally isomorphic to the orthocomplement of S because of the simple reason that H can be written as S direct sum the orthocomplement, if S is closed. If S is not closed, then also I can take the quotient and there is a quotient topology. What can we say about that? So, if S is not closed, then the natural topology in H mod S is not housed off. So therefore, this is the good case, that is the sort of bad case. Okay? Let us see what happens in the good case. Okay? Let us concentrate on the good case. So good case, and which is to say that this image of D bar is closed in kernel of D bar. that is to say, therefore it is closed in the whole L2 space itself, okay? So then if you look at the cohomology group HPQ L2 omega, that is, I'm just omitting the PQs and stuff for notational simplicity, kernel of D bar mod image of D bar, which is therefore, as people already pointed out, the image of D bar par. Yeah. So anybody knows how to represent this? If you have an operator and you take the orthogonal complement of its image, you get the kernel of the adjoint. Very good. And I will just, I already know that this is a subspace of D bar, but I'll just put that in just for security purposes. I mean, this is obvious, right? More or less. Just write down if you're familiar with it. Let's see. So therefore, this abstract object, this quotient, can be identified with those forms which are both D bar closed, means they are killed by D bar, and they are killed by D bar star. So they are called harmonic forms. So H or D bar harmonic forms. So this is harmonic forms. So now let us see how to find harmonic forms. In general, of course, on pseudo-convex domains, there are no harmonic forms if Q is greater than or equal to 1. But on non-pseudo-convex domains, there may be. So, L2 harmonic forms, L2 D bar harmonic forms, yes. Which one? It is true also for closed densely defined operators, yes.
And you don't have to say bar the plastic.
Is the same as, yeah. Yes, I'm going to come to that, yes. Actually, you have to, because the boundary conditions are going to be different. You take something which is simply connected but not pseudo-convex. Okay, so how does one find these? So we want to find exactly, a much stronger thing, yeah. So want to find all F in domain of D bar intersection domain of D bar star such that D bar F equal to 0 and D bar star F equal to 0. Right? This is our goal. This is to find harmonic forms. Now, to do this, let us recall the box operator. The box operator was D bar star plus D bar star D bar. Okay? And its domain is domain of box consists of those F in L2 PQ such that first of all D bar F must lie, first of all F must lie in my space. F is in domain of D bar intersection domain of D bar star. Okay. This is not such a big deal, but this involves certain boundary condition. Okay. And we want that D bar F, for this to make sense, D bar F lies in domain of D bar star and D star F lies in the domain of D bar, right? So this here is my complex Laplacian. And now it turns out that F, so I'll just state this as a proposition, F is harmonic if and only if it is killed by, I mean, by this I am also saying that it belongs to the domain of the Laplacian, which I did not write down, very precisely. Okay, maybe I should, because in view of this comment, F belongs to the domain of box. This is not a good box. It's a better box. and box acting on F is 0. Okay? One side is obvious, isn't it? If F is harmonic, right, you stick F in here, splits into 2 and each of them is killed, right? Other part is also equally easy. So now suppose if box F is equal to 0, then 0 is the same as box F, comma F, right? This is just ordinary L2 now, no weights or any business here, which is therefore d bar star, d bar F, F plus d bar star F, F, but F is both in the domain of d bar and in the domain of d bar star. So if I now integrate by parts, there will be no boundary term. And you are left with norm of d bar F squared plus norm of d bar star F squared. So which means that d bar F is 0 and d bar star F is 0, which precisely means F is harmonic. So therefore, the problem for non-pseudo-convex domains is to try to solve this equation with this this is the d bar Neumann boundary condition, and it's kind of difficult to deal with. So what I will do is to tell you about some domains in which this can be done. So some domains with known L2 cohomology. There are very few of them. And I already explained why, because, okay. So the ones we are considering they're called annuli. They're obtained by taking a domain and punching out another domain from them. So as you know, these are not pseudo-convex because, for example, Hartogs phenomenon occurs here, right? So, okay, so let me just go through what is known about these. So such a domain omega is of the form omega 1 minus omega 2 bar, where omega 2 is relatively compact in omega 1, okay? So then it is known, for example, just to give a sample, if omega 1 and omega 2 are both strongly pseudo-convex, I missed a R there, but you can still read it, are both strongly pseudo-convex, then, so we have, for example, we take a ball and remove another ball from it, right? So that kind of thing. Then, this group, H, P, Q, and we will assume here n is greater than or equal to 3. Let's start from there. H, P, Q, L2 omega is in degree 0, I didn't mention this, in degree 0, this you can easily check. In degrees, when Q is 0, let's say H 0, 0, you can check easily, H 0, 0, L2 omega is nothing but those holomorphic functions on omega, which are also square integrable, often called the Bergman space. So this is always an infinite dimensional space. So, and this does not depend anyway on the geometry of the domain omega. So HPQ omega is infinite dimensional for Q equal to 0. And also it is 0, and this is also a general fact always for Q equal to n. What happens in the middle is kind of interesting. It is infinite dimensional if Q is n minus 1, and 0 if Q is between 1 and n minus 2. One can show this. Say that again. Bounded, yes. Everything is bounded. Yeah, otherwise the first part will have trouble there, yeah. Bounded, yes. Everything is bounded, thank you. Okay. Lots of work has gone into removing the strong pseudo-convexity assumption. And it turns out something new happens here, which is not there in the pseudo-convex case. So right now, I think the best one can do, there is no condition on the outer boundary. This omega 1 can be any bounded pseudo-convex. The inner one is still pseudo-convex, but this one needs, at present, C11 boundary. So with these conditions, you can actually prove, again, the analog of the same result. You don't have to, and you don't need strongly pseudo-convex. C11 boundary and just weakly pseudo-convex. Just pseudo-convex. So this is what one can do here, okay? So that's an example, and all these are Hausdorff. All these groups are Hausdorff. So it boils down to solving that equation, but yeah. The last thing I want to say is to give a simple example in which n equal to 2 actually basically it is infinity and 0. Yeah, therefore, yeah. Infinity and 0, right? Yeah. Yeah, actually n equal to 2 can also be included here. The reason I wanted to say 3 is for 2 you need a slightly different method. But apart from, yeah, n equal to 2 is already correct. Yeah. The result is correct. Okay, and as my last example, let us look at the following domain. So we look at, in C2, you look at the following domain. So omega is the union of this guy. So this is the absolute space, mod Z1, mod Z2 space. This omega is the union of this guy, which is what? It is mod Z1 is between 1/2 and 1. And mod Z2 is less than 1. So we have this piece, and this piece over here is simply mod Z2 is less than 1/2 and mod Z1 is less than 1. Okay? So this is sometimes called the Hartog's figure. So this is another example of a classical example of a non-pseudo-convex domain. And what happens here, if you take a holomorphic function, it extends to the whole bidisk. That's what happens here, okay? So it is possible to compute the L2 cohomology of this guy also. So H, P, Q, L2 of omega for this domain, there is no surprises in degree 0. So here it is infinite dimensional and Hausdorff, namely the Bergman space, and this is 0, which is q equal to 2. Q equal to 1, something happens. This is infinite dimensional and it is non-Hausdorff, but even better than that, it is indiscrete. So remember what an indiscrete topology is. So there are, the only open sets are the empty set and the whole space itself. That actually is not so difficult to show, so you might want to try to see why that is the case. I think with that, I will end these lectures. Thank you very much for listening patiently.